Traveling waves. So, with this chapter, we are focusing on the wave equation that describes the nature of a traveling wave. And the equation looks like this: y of x of t. And specifically, we're describing the nature of a transverse traveling wave. The position y of the wave as a function of its x position and time is given by the amplitude of the wave times sine of kx minus omega t plus 5. So in this chapter, you're going to be using radians, so you should be in radian mode. So everything here, this could be, for example, meters or centimeters. Now this would therefore be meters or centimeters. So this would be the amplitude of the wave. Amplitude. This whole thing has to be radians. Radians. So if kx is radians, right, then what's the units of k? Well, x is meters, so it's going to be rads per meter. This is the units of the k. And then omega t is also radians. And then omega would be rads per second. And then phi is the phase angle. Phase angle of the wave, measured in radians. So the purpose of the phi is kind of you can think of it as a fudge factor that describes the initial conditions of the wave. What's the wave initially doing? So fudge factor describing initial condition of the wave. So what's the nature of omega and k? What do they mean? Omega is similar to the omega that we've had before. It's called angular velocity or angular speed, or sometimes called radial velocity. So we'll call it here angular speed. And remember, 1 over the omega is the frequency of the wave, right? Frequency is 1 over omega, so that's going to give you, frequency of the wave is omega over 2 pi, right? We've seen that back in chapter 15, right? Back in the oscillations chapter. So it's good to kind of have that as a foreground as you're doing this, because some of the things will carry forward, right? When you displace a spring from equilibrium, a certain mass, and you have k. This k is different. It's the spring constant of the spring. This k is not the same as the spring constant. Okay, so there's a little bit of confusion there. So then you displace the mass, then it goes back and forth, right? With a certain amplitude, a, negative a, right? And then you describe the motion of this as x equals a sine of omega t plus phi. Okay? So then the phi again is some fudge factor that describes the initial condition of the position of the block, you see. So the omega there has very similar definition to the omega here. It's also equal to, has units of radians per second, right? And then we can differentiate the x here. V equals a omega cosine omega t plus phi. So when you differentiate it, that gives you the velocity of the block as a function of time, right? And then when you differentiate it again, that gives you the acceleration. Negative a omega squared sine omega t plus phi, right? And then you usually say, well, what equation must this satisfy? So you find some kind of differential equation, which this equation is the solution for it, okay? So then you apply Newton's second law, F equals ma. So the force on the block is equal to the mass of the block times the acceleration of the block. And then the force on the block is equal to negative k of the spring times the position of the block, right? Negative kx. So then this ends up being a differential equation, right? So this one goes over to the other side. A is this function, right? And then x is that function. This is the position of the block, and this is the acceleration of the block. So if you put that in, you put this guy in here, plus k, and then you put this guy in there, right? And then you get here the sign. You can factor out the sign. You can factor out everything that's similar. So we can factor out the a and the sign. And then we get what? We get negative mw squared plus k, right? So then you're saying, okay, this expression must equal 0 for all values of t. Well, the only way it's equal to 0 for any value of t is if this term is equal to 0. So this is how you solve a differential equation. You generalize the solution, put it into the differential equation, and you see what conditions the omega must satisfy in order for it to satisfy that differential equation. Okay, and then you have here this must equal 0, and then you get here omega is equal to square root of k over n. So in that case, this is the frequency of oscillation of the block. The angular frequency must equal to the spring constant over the mass of the block, right? Then you can check to see if the units make sense. Because remember, it has to have units of radians per second, you see? So does the units make sense? Well, what's the units of K, the spring constant of a spring? It's units of newtons per meter, right? Kx is force, K is F over x. So the units of K is newtons per meter. The units of mass is kilogram. Now, if you take the square root of that, it should give you units of radians per second. Right? So unit analysis always helps when you derive something. So then you get here square root of, and then newtons is equal to kilogram meter per second squared, because that's the definition of a newton, divided by kilogram meter. Right? Kilogram and then this meter. And then the kilogram, meter cancel. You get square root of 1 over second squared, which is 1 over second. And 1 over second is radians. You see? So it's radians per second. So then from there to convert to frequency, you say what? You say radians per second. 2 pi rads is 1 rev or 1 cycle. Right? Cycles or revolutions is the same. So in other words, if I take W, if I take the omega and if I divide by 2 pi, that gives me cycles per second. Omega over 2 pi, so that's going to give me cycles per second, which is what we call hertz, right? So the same thing we can do for the frequency of a traveling wave. We can say frequency is omega over 2 pi, that's cycles per second, which is hertz, right? So in the case of this, what does the cycles per second mean? Well, if it has, let's say, frequency 2 hertz, it means the block makes 2 cycles per second. So in 1 second, it's gonna go, come back, that's 1 cycle, boom, boom. And then 2 cycles per second means it's gonna go, come back in 1 second. So something like that, that's 2 hertz per second, right? That's in 1 second, it has to do that twice. Okay, so 1 hertz will look like what? Right, a little slower, right? That should take 1 second. Half a hertz, it should go, in 1 second, it should just go to one, from here to here, right? So it's like this. And then like that. So if you can kind of mimic the motion with your hand, you're really understanding what's happening, you know? Half a hertz is slow, like that. 1 hertz is, right? 2 hertz is, and then so on like that. Kind of like the windshield wipers, right? So today's rain, you need a 2 hertz windshield wiper, right? Exactly like that. Now, when you invert the frequency, you get period. So for period, you could also do the same thing. So what's units of periods? So then you can say that's going to be seconds per cycle. So that means how many seconds does it take for this thing to make 1 cycle? It's just like opposite way of asking the question, you see. So if the frequency is 2 hertz, the period is going to be half a second. If the frequency is 1 hertz, the period is going to be 1 second. And if the frequency is a half a hertz, the period is going to be 2 seconds. So remember the half a hertz was like this, right? So half cycle per second means it goes like this in 1 second, right? So period 2 seconds means it takes 2 seconds to make 1 cycle. So it goes like this, and then so that's 2 seconds, right? So if it's 2 hertz, it's going to be like this. So it's going to take only half a second to make 1 cycle. So it's going to go and come back, and then that's half a second, like this, you see. So it's just, if this is large, this is small, and if this is small, that's large. So if we derive the equation for the omega of a block on the spring, then the frequency is going to be whatever the omega is divided by 2 pi. So it's going to be 1 over 2 pi square root of k over m. And then the period is going to be the reciprocal of that, 2 pi square root of m over k. Right? So I'm kind of doing a very quick overview of 15, because this chapter is very much based on 15. The next thing you've seen over there that we do is give you the average, the kinetic energy and the potential energy of the block, right, for energy conservation. So the potential energy is going to be what? Half kx squared. So the potential energy that the block has at any position along its path is given by the spring constant of the spring times the stretch amount squared, right? So when it's in the middle, it has no potential energy because the stretch amount is 0, see? And then the kinetic energy is going to equal 1/2 mv squared, right? So then if energy is conserved, what can we say? The potential energy at any point plus the kinetic energy at any point is going to equal what? Then we can set it equal to its maximum potential energy that it has when it's maximally stretched. So then that would equal to half Ka squared. Okay? And then that would equal what? Half cancel. Kx squared plus mv squared equals Ka squared. So this tells you that the potential energy at any point plus the kinetic energy equals to the maximum potential energy, right? So let's see, what was I going to ask here? So if we ask the question, what's the average potential energy? What's the average potential energy that the block has during its path? How would we answer that question? Average potential energy. And what is the average kinetic energy? So in other words, don't cancel the 2 for a second. Keep the 2 and we're asking this question. What's the average of this? And the average and the average. Okay? So, could we make the argument that since they're the average of this should equal to the average of that? The average kinetic energy and the average potential energy are the same? Yeah, because its energy is being conserved, so the average potential and the average kinetic should be the same, and the average of this is just itself because it's a constant, right? So then we're gonna make the argument that the average kinetic energy, the potential energy, is equal to the average kinetic energy. And therefore, if they're the same, that means twice one of them is equal to this, right? So that means the average kinetic energy is equal to a quarter of this, right? And then the average kinetic energy is going to equal a quarter of this. Then when you add them, that's going to give you half Ka squared. Okay? Now we could also look at this from a trigonometric point of view. More trig way. So what's the general equation for the potential energy as a function of x? Half kx squared, right? What's the general equation for x? This guy, right? So when I square this, what do you get? Now, what's the average of that value over one period? How do you in calculus? How do you calculate the average of that? The average of this is going to be half Ka squared times the average of this guy, right? Over what? One period of the motion, 0 to t, right? When I do this integral, it better come out half, right? It's gonna come out a half, because it should give me the same argument as from symmetry, right? From symmetry, I argued that this equals this, and then when you add them, they give you this, right? And therefore, one of them should equal quarter. So, I already know that this integral should give me a half. But if I want to do it without, let's say I don't know the result, so I want to do this just from scratch, what would I do? Then I could do the double angle formula. What's sine squared? 1 plus sine of 2 theta. Over 2, is that the double angle? Cosine squared is? What's sine squared?
1 minus cosine.
Oh, then I have to use the double angle. So sine squared doesn't have a double angle square formula? Or maybe it's 1 minus sine?
1 minus.
Huh?
1 minus.
Oh, 1 minus, okay. Then I integrate that from 0 to t, so the 2 comes out.
Should be cosine.
Oh, it should be cosine? Okay, then you're gonna now integrate this, you get t. Integrate cosine, you're gonna get sine. Then when you integrate this, you're gonna get what? Sine of this, and then 2 omega is gonna come out and down to the bottom, right? From 0 to t. Oh, you know what I forgot? When you do the integral, you have to also divide by the time interval, right? Divide by that. So it's like integral of the function, right, over the interval itself, right? So then you have over the period. So then what happens when I put the period here? And when I put the period here, what's going to happen? Omega t. But then what's omega t? For our purposes, the phi doesn't matter in this integral. It's just the phase angle. All that matters is the 2 omega t. So then you have 2 omega t, where t is the period. Right? Now when I put 0, that gives me 0, and this gives me 0. Right? So that's gone. So now, then on the bottom I also have t. So well, now what's this? Remember, omega is what? 2 pi f, right? Remember? Because f was omega over 2 pi. And then the period is what? 1 over f. So omega t is what? Omega t is just basically 2 pi f times 1 over f. Cancel. So omega t is just 2 pi.
Since the t is inside the integral,
Say that?
t on the bottom. You said it's over t, and you put it inside the integral. Would you have to just make that too?
Oh,
I don't think that t is inside that.
no, it's the integral divided by the
Okay, since you put it inside.
Huh? I put this here?
Oh no, use the one in the bottom where you divided the whole thing by 2. Yeah,
Yeah, it has to be outside.
it's outside. Yeah.
Yeah, it's not, maybe I didn't write it good. Yeah, it can't be inside the integral. Because remember, the average of a function is going to be integral a to b f of x dx over b minus a. It's outside. So there's a lot of stuff going on here, integration, trig, and stuff. Well, this ends up being just 0, right? Because omega t is 2 pi. Sine of 4 pi is 0. What was that? This is pretty deep stuff. Okay, so now we get the period, cancels the period, quarter a squared, quarter 1/4 ka squared.
Why is phi gone right here?
Huh?
Why is phi gone?
Well, after you take the derivative.
Yeah.
Where did phi go? Oh, phi doesn't matter.
Oh, okay.
Because even if phi is some other number, then we're gonna go from that number to the add the period.
Okay.
Yeah, so I
Oh,
assume
okay.
phi is 0.
Got it.
Because phi is a fudge factor.
Gotcha.
Yeah. Okay, so we're gonna do similar kinds of things now in this chapter. So you have here K. This K is gonna be different than this K. This is the spring constant. So this is the more newer aspect that we don't have in chapter 15. The omega is similar to the omega of chapter 15, but this one is slightly different. It's called the wave number. So its units are radians per meter, wave number. Whereas this one is called the wave angular frequency. Wave angular speed, omega. Okay? So now let's describe the K is, as I said, the K is like the more newer concept. So to understand what each of these does and what they mean, what you can say is, let's write down K is equal to, assume K is 1 radian per second and omega 1 radian per meter, and omega is 1 radian per second. And let's assume the amplitude of the wave is 1 meter, and then let's assume the phase angle is 0 rads. Right? So whenever you have something like this that is kind of newer to you, that's one of the best ways to analyze it, is give these random easy numbers, and then give this 1 meter, and then draw what that wave would look like. So y of x of t, it would be what? Sine of, since the amplitude is 1, you're just going to have sine of x minus omega, sine of x minus t, right? So now what I can do is I can write different progressions of that wave as a function of time. So I can say, what is that wave going to look like at t equals to 0? So at t equals to 0, the wave is going to look like this. At t equals to, let's see, I'm going to choose seconds that are multiples of pi, so it'll be easier to draw this. I'm going to say at t equals to pi over 2 seconds. And you go, what does that mean, pi over 2 seconds? Well, it means 3.14 over 2, that's 1.57 seconds later. So it just makes it easier for us to graph that wave, right? So rather than choosing 1 second, 2 seconds, 3 seconds, I'm choosing time intervals that are multiples of pi seconds, right? So that wave will look like this. At t equals to pi seconds, y of x of t is going to look like sine of x minus pi. And then at t equals to 3 pi over 2, the y of x of t is going to be sine of x minus 3 pi over 2. And then by the time we get to 2 pi, it's probably going to look like the same thing, right? Back to the same. Now graph all of these functions. So preferably if you have a colored pencil, colored marker, you could draw these in 4 different colors. Maybe I could go bring, I have a red here.